Hello everyone, thank you for joining us for our final presentation. We are Team Fireflyers and we are very happy to have you here today. I'm Muriel.
I'm Najwan.
I'm Anna.
I'm Alex.
And we do not have with us, but our other team member is Izzy.
In reviewing the initial problem statement for the 2026 National Design Competition, which was cold weather limb warming devices, a brief overview of the prompt. In winter sports, para-athletes will remove their prosthetics during training and competition, leaving their residual limbs vulnerable to cold, environmental conditions, such as stiffness and injury. And our objective as a team was to engineer a high-performance residual limb warming system for para-athletes.
As for the market gaps, there's no active prosthetic integrated warming system. Athletes have been using hand warmers to stay warm. So our device provides the solution for active controlled heating. It's designed to work in cold environments and it works on top of an existing liner or without it. It maintains a safe warming temperature. How it's different? It adds function without changing the prosthetic fit and it's easy adoption for the user. For the life cycle, it's designed for repeated use as it's simply battery charging. Its expected lifespan is multiple sessions. It's waterproof and moisture wicking materials used. It's durable and flexible. For the user care, it's removable. The inner liner is machine washable and the outer surface is wipeable. How does the user put it on? It's easily slid on the residual limb and is tightened with a Velcro strap around it.
In reviewing our final design before we go into the specific specifications surrounding each step, there were three main parts that we went through. So the first was the initial finite thermal element testing, or FTE. This was where we basically tested our concept just to see if our insulation idea would work. So what we did was we created a CAD model and we performed finite thermal element testing on it just to make sure that an applied heat source could be maintained for a specific period of time, in this case 1 hour. And this was just a base concept to make sure that our idea would work, and because it succeeded, we moved on to the next step, which was exploding it into an entire CAD model where we basically made a shape similar to what we wanted for our final design using the shape of our athlete's limb as reference, and we basically made it into an entire sleeve limb, tested finite thermal element testing again and made sure nothing changed, and because that went well, we then moved on to our physical model, and this is actually our final project, which reflects both of these tests quite well, and as of this recording, it can maintain the heat just as it did in the CAD testing, and it can reach its maximum heat in under 20 minutes.
First, we'd like to start with the overview of our device specifications. So this device is meant to heat the residual limb of the athlete and is fitted to their specific measurement. And as a safety, it will not exceed 104 degrees and maintain a constant temperature in cold environment. Ideally, this would hold charge for 5+ hours and is moisture wicking and thermally insulated. This design is also universal and can be scaled to fit other athletes' limbs. It is also safe to use, affordable, and easy to replicate. Next up is the specifics of the electronics. So to the right here, we have labeled the diagram of our wiring. So first, number one is our battery with variable voltage, which outputs 15 volts due to our PD board. Second is we have a 9-volt battery and switch that powers the microcontroller. Third, we have the load, which is our heating wire that is divided into 2 sections for the front and back of the sleeve. Fourth is the MOSFET gate, which controls the power flow from to the load when activated by the microcontroller. And 5, the microcontroller, which interprets data from our sensors and relays this signal to the load managing board. And finally 6, our sensors, which monitor the temperature and influence heat output via our PID controller. Next is a summary of our safety features. First, our electronics are housed in a potting compound and a waterproof pouch for protection. Second, we have a PID, which is an error-based output controller, which calculates our output as we move towards our target temperature. This is highlighted in the code for your better understanding. Third, we have an automatic power shutoff system in place if the temperature were to reach our safety threshold and if the sensors were to error. First, please consider these 4 constraints that we've set. That is, the min temperature is 94 degrees, our target temperature is 96 degrees, and our safety temperature is 98 degrees, all in Fahrenheit. Now, if we take a look at the active monitoring of the 4 thermocouples that are embedded into the system, you can see that the front has thermocouple 1 and 2 on it, and the rear one has thermocouple 3 and 4. So, when the temperature first is assigned based off of whichever is the max between the 2 thermocouples on each side. Next, until the temperature reaches the minimum temperature, which in this case is 94 degrees, it will operate on max, which if you saw before, it popped up as 255 at the output. But once it passes that, it'll switch to a PID system, which is, you can see now there is a much smaller adjusted output that will try to bring it closer to a temperature of 96 degrees. In addition, so you can see right now both are actually settled between 1 degree of our target. And finally, if this temperature were to reach 98, it would quickly shut off that function, and we wouldn't have any power going to either heating side. Next, we have some statements in here. So whenever the sensors have an error, they will result to a measurement of 32. In case of this situation, this will also be set to 0.
In order to prove that our device was safe and able to work, we performed several tests that replicated those at competition, such as hotspot, performance, electronic safety, and user comfort testing. These consisted of qualitative and quantitative results that will be discussed next.
First, we completed our hotspot testing. We did this by heating up the sleeve for 10 minutes and then measuring at several locations. And our ambient temperature during this test was around 75 degrees, and the initial battery charge was 99%. During this duration, the battery charge decreased by less than 1%, and we were to identify a few potential hotspot locations. Next up was the results of our performance testing, which ran over a 20-minute duration. So one of the things we learned here was that the temperatures averaged in the 80s. The temperatures did not exceed the safety limit during this duration. And although there seems to be a slight disparity in the temperature, this is likely due to poor sensor placement, which may have been caused by the fact that we did not have a thermal imaging camera to use in the previous test. Additionally, we were able to identify a battery power cycling issue through this test by seeing how the temperature declined in a repetitive and organized fashion. Next was our electrical safety. So we have all of our wires insulated and sealed into waterproof materials, and we also tested with multimeters.
To replicate how our athlete would don the device, we applied the device to each of our arms to determine how comfortable or how the device would fit. We added that soft insulating material on the inside of the device so that the user's skin would not touch any of the wires or the electronics. Also, all the seams are finished along the device, allowing for a smooth and clean profile. We were allotted a total budget of $1,500 to make our device. However, with the cost of prototyping being a little bit larger than the actual unit cost at $303.66, The total cost of the device is around $722. As you can see here with our itemized list of all the equipment and material used to build our prototype. For commercialization analysis, we determined that our design is at a 6, a full-scale prototype field demonstration, as our prototype is an easy-to-use, fully functioning device.
In regards to future work, there are a couple of areas that we determined could be used to advance the product, such as heating modes, adding selectable heating options of high, medium, and low. In regards to weight, the original prototype was heavier than intended due to waterproof material and a bigger battery than originally intended. Wiring, such as different testing wires for potential improvement of meshing, or vertical weaving for a better flexibility of the product. In regards to electrical setup, we could minimize the entire setup for a more compact system, and we could change to a programmable battery in the future. The final steps we're going to take to make the product market ready include polish, including recreating the sewing pattern and uploading it into a sewing software for easy stitch replicability. Development of a standard epoxy mold for electronic could improve the barrier for electronical systems in the future. Installation of a more lightweight battery system, utilization of a thinner fabric between heating wire and user limb, and electrical access for machine wash purposes. Thank you very much for joining us.